out of the way. Everybody should be seeing my document camera at this point. Paris and Sulphur Springs, if you're not, let me know. So I think we have looked at maybe one problem at the very, very end of class last week where we actually had a variable in a denominator like this. So when you get to an equation like this, these are the ones that are properly called rational equations. This is a rational equation. It's not just that there are fractions in it, it's that at least one of those fractions has a variable on bottom in the denominator. For my Monday night guys, the guys that were here Monday, we did some of these problems. I tried to make sure I picked different problems tonight from the ones we did Monday night, just so y'all don't have to sit and watch the same things. And I'll try to get through these as quickly as possible, but we got to make sure we know how to do these things. So, okay, really and truly, it's the same idea. Have I got the bottom? Yeah, I do. It's kind of the same idea as what we were doing with those fractions last week. We want to multiply both sides of this equation times the LCD. And when we do, that's going to get rid of all these fractions. So to figure out what the least common denominator is, well, remember, anything that appears as a factor in any of these denominators has to appear as a factor in the least common denominator. Well, this is 2 times x, right? So we have to have a factor of 2. I don't know what number x is, but this is 2 times x. Whatever number x is, that number is a factor in this denominator. So I know my LCD has a factor of 2, and I know it has a factor of x. And then when I look at the next denominator, well, I know I have to have a factor of 3. So I'm going to add that into my LCD. I know I have to have a factor of x, but y'all see I've already got that covered, right? And then when I look at this last denominator, I have to have a factor of 3, but notice I've got that covered as well. Y'all see? Everybody see that? So if I multiply this stuff together, that's my LCD. 3 times 2 is 6. 6 times x is 6x. That's our least common denominator. Does everybody see that? Because we definitely need to be able to find the LCD. And now all we're going to do is multiply each side of this equation times that least common denominator. And this is super easy if we start with the right-hand side, because that one doesn't have, we don't have to distribute on the right-hand side. So just to see how this works. Remember, when you multiply fractions, we're thinking of this as if we're multiplying the fraction 22 over 3 times the fraction 6x over 1. When you have common factors on top and bottom, you can cancel them. Well, notice 3 is a common factor. It's certainly a common factor of 3. It's also a factor of 6. So we can cancel that 3. And of course, that's the entire point, is we're going to wipe out these denominators. So we can just say that 3 divides into 3 one time, 3 divides into 6 2 times. Everybody see that? And so that 2x over 1 is just 2x, and 22 over 1 is just 22. So all I'm left with there is 2x times 22. And 22 times 2 is 44. 44 times x is just 44x. So everybody see that that's now what we have on the right-hand side. We're going to actually do the exact same thing on the left side, except we have to do it twice. We're going to have to do 6x times 7 over 2x. Then we have to do 6x times negative 5 over 3x. Everybody see that? So when I multiply 6x times the 7 over 2x, well, I can cancel a 2, right? 2 goes into 2 one time, 2 goes into 6 3 times. I can also cancel that x. Do y'all see that? Again, I don't know what number x is, but I know that I have a factor of x on top and a factor of x on bottom. That's common, so I can cancel it. So notice when I do that, just leaves me with 3 times 7, which is 21. just the number 21. Everybody with me so far? Now, the only thing you got to remember is we're distributing. We just did 6x times 7 over 2x, but now we still have to do this 6x. We still have to multiply it times negative 5 over 3x. When we do that, notice we can cancel a 3 on top and bottom. 3 goes into 3 one time, 3 goes into 6 2 times, right? And again, we have x's on top and bottom, so that's a common factor we can cancel again. We can cancel that x on top and the x on bottom. And when we do, that literally just leaves us with the number 2 multiplied times the number negative 5. 2 times negative 5 is negative 10. So everybody see what we did to get rid of the fractions? Of course, here, like I say, it's kind of two things that's happening. A, we're getting rid of the fractions. B, because we got rid of the fractions, that gets that variable out of the denominator where we can actually sort of get a hold of it to solve the problem. So at any rate, now all I'm going to do is say that, first of all, 20, by the way, make sure you always do any arithmetic, to simplify as much as you can first. We're going to go ahead and say that 21 minus 10, of course, is 11. So I have 11 equals 44x. So now all I have to do is divide each side by 44, right? When I do, I get x by itself on one side of the equation. On the other side of the equation, I have 11 over 44, but do y'all see that if I simplify that as I should, that's 1/4, right? 44 is 11 times 4. So 11 goes into 11 one time, 11 goes into 44 4 times. Incidentally, if this problem were in the homework and you answered 11 over 44, it's going to tell you it's incorrect. I think when it gives you the hint, when it tells you it's incorrect, I think it will say, make sure you simplify all fractions in your answer. But whether it does or not, it won't give you credit for this. It'll want you to simplify before it gives credit. Everybody with me there? Okay, so that's the basic idea for these. Now, I just want to do a couple more and look at how these might look a little different. So here's one. Now, in one way, this looks a little trickier because notice this denominator is not just like 2 times x or something, or 3 times x. It's actually two separate terms. It's x plus 1. What makes this easier, so that makes it maybe a little trickier than the last one we did because it looks a little different. What makes it probably easier than the last one we did is I actually only have one denominator, right? And if you only have one denominator, clearly that's your least common denominator. And so x plus 1 literally is our LCD. By the way, I know that seems weird because when you think of the least common denominator, you're thinking of stuff you multiply together to get a number that is your LCD. Well, these aren't things being multiplied, they're being added. But the way to think about it is x plus 1 is just some number, right? And so, for instance, if x turns out to be 2, then this denominator is just the number 3, for example, right? And if this were the denominator 3 and this were the denominator 3, that's our LCD. We'd multiply both sides times that. So it's, again, that thing of, I don't know what number x plus 1 is, but I know it's some number, and whatever number it is, that's the LCD. And so I'm going to multiply both sides times x plus 1. And here I've got an x plus 1 on top and a factor of x plus 1 on bottom, then I can cancel that. And so that just leaves me with 1 times 8x, which is simply 8x. I need to put a piece of paper between those. Sorry. You can do the same thing on the other side. Now, on the other side, I want y'all to look ahead a minute here. So notice when I distribute this, so I'm going to do x plus 1 times 4. Then I'm going to do x plus 1 times negative 8 over x plus 1. Now, I'm sure y'all can all see that when I do x plus 1 times negative 8 over x plus 1, I'm going to do just like I did on the left side. I'm going to cancel those x plus 1s, right? But when I multiply the x plus 1 times 4, I can't cancel anything. Do y'all see that? So when I do that part, y'all look, all I'm going to do is when I do x plus 1 times 4, really all I'm doing is I'm distributing 4 times x plus 1. Everybody see? So 4 times x is 4x, and 4 times positive 1 is positive 4. Am I good with that? And that takes care of multiplying the x plus 1 times 4. When I do x plus 1 times negative 8 over x plus 1, again, that's a common factor on top and bottom. I just cancel that x plus 1. And that just leaves me with 1 times negative 8, which is negative 8. Y'all see? Actually turned out to be pretty simple once we see what's going on. Over here on the right side, I should go ahead and say that 4 minus 8 is negative 4. So I have 8x equals 4x minus 4. Everybody with me here? Okay, now I'm going to subtract 4. We're just going to solve this little equation. I'm going to subtract 4x on each side. You know, since my constant term, negative 4, is all on the right side, I'm just going to move my variable term all to the left. 8x minus 4x is 4x. On the other side, 4x minus 4x, of course, is 0. That cancels. I'm just left with negative 4. And I need to now divide each side by 4. Does everybody agree that negative 4 divided by positive 4 is negative 1? And so that's our solution. Let me zoom out just a little because I want us to be able to see all of this on the page at once. Hang with me. So remember our original equation. Let me write it again because I've marked through so much stuff you can't hardly see what it was. So remember, that's our original equation. We solved it. We multiplied both sides times the LCD, solved it. We got x equal negative 1. So we, draw a little smiley face. We write I heart math. That requires a double exclamation point, a little lightning bolt under it, like that. And we move on to the next problem now. Here's the sad thing about this. If this were a problem on a test and you did this, when I graded it, I would have to make your little smiley face, a little sad, frowning face with little tears. Or maybe those are tattoos of the guys I shanked in prison, I don't know. I'd have to break your little math heart, and I'd have to do something in red ink like x minus 2 or something like that, I don't know. What I'm saying is this answer is incorrect. So then the question is, can anybody see where I made an error? Let me save you some time. You will not see where I made an error. Why? Because I never make errors. That's kind of a joke, but kind of. But in this case, I didn't make an error except sort of in judgment. So there's something about these rational equations I haven't told you yet, and I need to tell you. It turns out to be important. The answer I should give here, instead of saying that the solution is x equal negative 1, I should say that there is no solution. Let me tell you why. I tricked you with this. I didn't trick you. I just didn't give you all the information you needed. Kind of did this on purpose because I want this to stick with you, because This is a mistake students make sometimes, and they just never even think about it, and I sort of get why. If you get to this solution, x equal -1, you've done some pretty decent algebra to get there. There is one problem, though. Remember how technically we should always check our solutions in the original equation? I mean, really more than just technically, we really just should. It's just I'm not naive enough to believe that students always do. So I'm saying technically we should. Here's the thing. I'm confident we didn't make any mistakes. We didn't make any arithmetic errors. We didn't make any algebra errors. But if I go back to this original equation and check my work, in other words, I'm just going to plug -1 in place of x everywhere I see it in the equation and check to make sure that I get a true statement. Let's take a look at what happens. So I'm just replacing that x with -1. Yep. Sorry, that's a 1. Okay, so I've got 8 times -1, which is -8, over, what's -1 plus 1? 0. This is an easy one, right? Equals 4. Negative over negative is positive, so that's going to be plus 8 over, oh, there's another -1 plus 1, 0, right? Let's just look at this one. What is 8 divided by 0 equal to? What's 8 divided by 0 equal to?
0.
I'm hearing a lot of zeros.
Undefined.
It is not 0. I think I heard somebody in Paris say that it is undefined. Is that what you said? If it's not, tell me that's what you said. It'll make you sound smart. It's undefined. 8 divided by 0 is not 0. 8 divided by 0 is, there's no such number as 8 divided by 0. So let's talk about why, because this is an issue that's going to pop up again, probably at least when we talk about slope of a line, it's going to definitely pop up, but I think it's even going to pop up in more places than that. So let's talk about 8 divided by 0. First, let's talk about something like maybe 8 divided by 2. What's 8 divided by 2 equal to? 4. I agree, it's 4. Easy. Here's a little trickier question, though. So 8 divided by 2 is equal to 4. That's an easy question to answer. Here's one that's a little bit trickier. Why is 8 divided by 2 equal to 4? Why? Wait, I know your first thought is going to be to say because 2 goes into 8 4 times. And I agree, 2 does, quote, go into 8 4 times. But when I say 2 goes into 8 4 times, didn't I literally just say 8 divided by 2 equals 4? That's just another way to say 8 divided by 2 equals 4. So it's sort of like me saying 8 divided by 2 is equal to 4 because 8 divided by 2 is equal to 4. How about this reason? The reason that 8 divided by 2 is equal to 4 is because 2 times 4 is equal to 8. And I think we might have talked about this. If we didn't, we might have talked about it the first week in our Monday class. Either way, we got to make sure we know what's up here. Every division problem is asking you a question about multiplication. So when I write 8 divided by 2, that's just, think of it like this. That's kind of a shorthand way for me to say 2 times what number is equal to 8. Y'all see what I'm saying? So 8 divided by 2, every division problem is asking us a question about multiplication. 8 divided by 2 is asking the question, 2 times what number is equal to 8? And of course, 2 times 4 is equal to 8. And that's actually how we check division problems, right? When we say that 8 divided by 2 is equal to 4, we literally check that by checking to see if 2 times 4 is 8. So 8 divided by 0, do you see why that can't possibly be equal to 0? Because is 0 times 0 equal to 8? No, it's not. Then this must be the wrong answer. 8 divided by 0 is literally asking us, what number do I multiply 0 times to get 8? Do you agree there is no such number? It doesn't matter what number. Let's say I put 8 out here. Well, 0 times 8 is an 8 is 0, right? Dak Prescott. Nope, he's not the right answer. Possibly not for the Cowboys either, but certainly not for this problem. 0 times 4 is not equal to 8, but it is equal to 0. The point is, it doesn't matter what number I write here. 0 times that number is always going to be 0. It's never going to be 8. Do y'all see that? That's why we say that 8 divided by 0 is undefined. In this case, undefined literally means when I say 8 divided by 2, I'm describing some particular number. And that number happens to be 4. So this is 8 divided by 2 is defined to be the number 4. 8 divided by 0 is undefined because there is no number that it defines. Y'all see that? There's no number you can multiply 0 times to get 8. Now, on the other hand, 0 divided by 8 is equal to 0. That's the perfectly correct answer. Why? Because 0 divided by 8 is saying 8 times what number is 0? Well, 8 times 0 is 0. So the point is, anytime you divide 0 by a non-zero number, you always get 0 for the answer. But anytime you divide any number by 0, it's always undefined. And you got to keep those two straight. It'll really mess you up if you get them twisted. That's why it's always good to think about what division means. Like 6 divided by 2. It's good to think about that and say, oh, it's asking me 2 times what number is 6? It's 3. That way, if you get these mixed up and you go, oh, 8 divided by 0, I can't remember. Is that the one that's 0 or is that the undefined one? You can check for yourself. Is 0 times 0 equal to 8? No, it's not. Oh, this is the one that's undefined. Everybody see what I'm saying there? So you got to keep those straight. Finally, the last little thing I'll say about that before we work through another problem. What if you have both things going on? What about 0 divided by 0? What's that equal to? So if you have 0 divided by a number that's not 0, you get 0. If you have a number divided by 0, it's undefined. Well, here I have 0, but also divided by 0. What's that equal to? Zero? Well, do y'all agree that 0 times 0 is equal to 0? Then I guess we could say that 0 divided by 0 is 0. Wait a minute. I'm going to make a different argument. Why couldn't 0 divided by 0 be 1? Don't we always say that any number divided by itself is 1? I mean, 0 divided by 0, that's a number divided by itself. 1 divided by 1 is 1. 2 divided by 2 is 1. 3 divided by 3 is 1. Why wouldn't 0 divided by 0 be 1? And what if I say that 1 is the answer? Well, y'all look, I can check my work. Look where I'm pointing. Is 0 times 1 equal to 0? Is 0 times 1 equal to 0? Yeah, that's the right answer. Hey, maybe Dak is the right answer. Is 0 times 4 equal to 0? Of course it is. Maybe we should have tried Shador. But maybe that's Roger Staubach, but y'all aren't old enough to know who I'm talking about. Look, this could be the right answer. 0 times 12 is 0. Do y'all see that we have kind of a problem with 0 divided by 0? And that problem is, remember how I said 8 divided by 2 is describing one particular specific number, the number 4? The problem with 0 divided by 0 is that you can't tell me which number I'm talking about here, because it doesn't matter what number you choose, it's going to look like that's what 0 divided by 0 is. You know, what if your favorite number is 13 because it's proven to be so lucky down through history? Well, 0 times 13 is 0, so I guess that could be the right answer too. So the upshot of that is 0 divided by 0 is also undefined. There's a slightly different way of looking at it. You know, 8 divided by 0 is undefined because there is no such number. There's no number I can multiply 0 times to get 8. 0 divided by 0 is undefined because it is not well defined. And in this case, what a mathematician would mean when they say it's not well defined is that we know that every division problem is supposed to have exactly one answer. This one, the answer is just arbitrary. You could use any number you want. Everybody see that? So for that reason, basically, anytime you're doing division, if you're dividing by 0, it doesn't matter what's being divided, it's undefined. Anytime you're dividing 0 by a number that's not 0, the answer is always 0. Everybody with me there? So, okay. Sorry that was long-winded, but that's something that's going to be good for us to kind of know when we get to slope and a few other things. So back to our problem here where we were checking our work. And so we had plugged our proposed solution, -1, in. And when we do, it turns out that our entire equation becomes undefined. Do y'all see that? There's no such thing as division by 0. So for that reason, here's how you have to look at these rational equations. You go through this process to solve it. You multiply both sides times the LCD to clear the fractions. You solve the equation, but when you get this solution, well, here's how you have to think about it. You have to think about it like this number. When you get this number, in this case x equal -1, what you need to say to yourself is, if this equation has a solution, this number is the only candidate. This is the only possible solution. So don't get here and say this is the solution. Say this is the only possible solution. You still have to check it. Now, for those of you who, as I alluded to earlier, know that you should check your work, but you really don't like to be bothered to check your work, I will say this. If you haven't made any errors, arithmetic or algebra errors in getting to this solution, at the minimum thing you have to check is you have to look to see if plugging this number in for x would make any of these denominators 0. If it makes any of these denominators 0, and of course -1 makes both of those 0, then what that means is the equation has no solution. That's just how it is. There's a reason why that can happen. Maybe we'll see another problem. Maybe we'll look at that on another problem. There's actually a reason why that could happen. We did everything right. We did everything the way we were supposed to do it, but we still arrived at something that looked like a solution that does not solve the original equation. There's a reason why that can happen, but the bottom line on it is that means that every time you solve one of these rational equations, you have to check and make sure that whatever you get, it doesn't make a denominator 0. Okay, let me move on to another problem. We're going to solve just a few more of these. I want to make sure y'all have seen enough of these to be pretty comfortable with what we're doing. So, okay, here's one. We're going to have to start getting into something called factoring polynomial. On Monday class, we talked just briefly about this. We'll talk briefly about it again tonight. Probably next week, we'll have to spend a little bit more review time with it, as much as we can anyway. But for now, I just want to kind of give you some basic ideas about factoring polynomials. And this turns out to be a real simple one to start with. But if we're going to solve this, and we've got these denominators, and we have to find the LCD. So here's the thing. 2x minus 2. I don't know what that number that is, but I know that that has to be a factor of the LCD. I know that 2 has to be a factor of the LCD. I know that x minus 1 has to be a factor of the LCD. So then the question is, does that mean that my LCD is going to be 2x minus 2 times 2 times x minus 1? That's a lot. Sometimes you might have to do something like that. It turns out in this problem we don't, and here's the trick. Look at this first fraction, the 3 over 2x minus 2. See if you agree that that is the same as what I'm writing now. You all agree that 2x minus 2 is the same as 2 times in parentheses x minus 1? What I'm doing here is I'm distributing backwards. Do y'all see that? Like, it's pretty easy when you look at this to see that, oh, 2x, that's 2 times x, and oh, here's negative 2, that's 2 times negative 1. There's a factor of 2 in each of these terms, right? So we would say that 2 is a common factor of the terms in this denominator. Anytime you have a common factor, you can factor it out. And so and basically that just means you can distribute backwards. So all I did is I said 2 is a common factor. So I'm going to write that 2. And then to figure out the x minus 1 over here, all I'm doing is saying, well, what would I multiply 2 times to get 2x? Well, duh, I'd multiply 2 times x to get 2x. And what would I multiply 2 times to get negative 2? Oh, I'd multiply 2 times negative 1 to get negative 2. Does everybody see how I did that? So like, for instance, if you had something like, let me come somewhere where I've got some room. If I had something like this, well, does everybody see that 5 is a common factor of each of these terms? Like this first term is 5 times x. This second term is 5 times 3 or 5 times negative 3. So there's a 5 in each term. I can factor it out. And then I just have to say, okay, well, what would I distribute this 5 to get 5x minus 15 back? I'd multiply 5 times x to get 5x. I'd multiply 5 times negative 3 to get negative 15. So 5x minus 15, if I factor it, that's what it looks like. Everybody see how we're doing this? So, okay. The reason you want to do that is because once you do, do you agree that once you do, it's pretty easy to see that this actually is the LCD? So we know that our LCD has to have a factor of 2. We know it has to have a factor of x minus 1. In this denominator, we have to have a factor of 2. Well, we already have that, right? In this one, we have to have a factor of x minus 1, but we already have that. Then that is our LCD, 2 times x minus 1. Every factor that appears in any of these denominators is covered if we just use 2 times x minus 1. Everybody see that? So, of course, I've got to multiply both sides times that. I didn't leave a lot of room to do that here, but I'll give it a try. Before I actually start solving this, let's do something smart. Before we get this all crossed through and marked up. Yes, sir? Okay, good deal. Thanks. Before we get this all crossed through and filed up, while it's still easy to do it, what would I need to replace the x with here if I wanted to make that denominator equal to 0? 1, does everybody see that if I plug the 1 in for x, 1 minus 1 is 0, and I'd get 2 over 0? What about in this one? What would I replace x with to make that one 0?
1.
1. If you just look down here, it'd probably be easier to see that maybe. You see that 2 times 1 is 2 and 2 minus 2 is 0. So if I replace x with 1. So I'm going to go ahead before I even start solving this equation, and I'm going to make a note to myself that x cannot be equal to 1. Everybody see that? That will help me, because now when I solve this equation, if I get down here and I get x equal 1, I'm not likely to just draw a box around it and think I got the right answer and move on. Hopefully by me looking first to see that, oh, if x turns out to be 1, that means there's no solution, because x can't be 1. It would make some of these denominators 0. When you work these problems 10 through 15 in the homework, they're going to ask the question as a two-part question, and the A part is there's a couple of different ways they could ask it. One way they ask it is list or state any restrictions on the variable. Restrictions on the variable. Well, 1 is a restriction on the variable x. In other words, x is restricted from being equal to 1. X isn't allowed to be equal to 1. That's what they're asking. Or sometimes instead they might say list any values of the variable that make any of these denominators equal to 0. It's the same thing, right? Either way, if this were a problem in the homework, in part A, they say, whatever, list any restrictions on the variable. There's one restriction on the variable. It's 1. X cannot be equal to 1. Everybody with me? Now when we solve this thing, when we get to our solution, if we get 1, we know to say there's no solution. If we get anything other than 1, and we're confident that we haven't screwed up somewhere, made a mistake, then we'll know that is the solution. Because as long as our solution isn't equal to whatever this restricted value is, it'll always be the correct solution, unless we made an error somewhere. Okay, so anyway, now let's roll through this. Okay, so when I multiply the LCD times this first term, everything on top and bottom cancels. Y'all see that? The 2's cancel, the x minus 1's cancel. I'm just going to be left with 1 times 3, which is 3. Everybody good there? But then when I multiply all of this times this next term, the 1/2 term, that time the 2's cancel, but the x minus 1 doesn't. Y'all see? So I've got x minus 1 times 1, or 1 times x minus 1. Of course, that's easy enough. 1 times x is x, positive x. And positive 1 times negative 1 is negative 1. So I've got 3 plus x minus 1 after I multiply the left side times the LCD. Everybody with me? Okay. On the other side, now notice here the x minus 1 factors are going to cancel, but that 2 isn't. So I'm going to have actually 2 times 2, which is 4, right? So now, let's go ahead and combine these like terms here, the 3 minus 1. So I've got an x over here, and then 3 minus 1 is positive 2. So x plus 2 equals 4. By the way, if you wrote 2 plus x equals 4, that's fine. It's the same thing. Do y'all see that all I need to do now is subtract 2 on each side to be done with this thing? And so when I do, x equals 4 minus 2, of course, is 2. Notice that's not our restricted value, so this is the correct solution, unless I've messed something up, which I don't think I did if I check it real quick, and I'm going to just real quick. If I plug 2 in here in place of x, 2 times 2 is 4, 4 minus 2 is 2. So I'll have 3 over 2 plus 1 over 2, right? So that's what I have on the left side. And then on the right side, if I plug 2 in here, 2 minus 1 is 1, so I get 2 over 1. So I get 3 over 2 plus 1 over 2 equals 2 over 1, which is 2. Does everybody agree that 3 halves plus 1/2 is 2? 3 halves plus 1/2 is 4 halves. And 4 divided by 2 is 2, so it works. I'm just saying, I don't typically check my work, but since there is some concern now after we saw we can do everything right and still get the wrong answer, but what I wanted to show you is if you've done everything right, you haven't made errors, this will always be the correct answer, as long as you don't end up with one of these restricted values. Here's why that can happen, by the way. You know, if we go back up here to the top, when we multiplied this times that LCD here, and then we did it over here, remember, we keep saying, okay, at this point, we don't know what number X is, but we know what number, whatever number it is. For instance, X minus 1 has to be a factor of the LCD and so on, right? Well, here's the problem with that. Because we don't know until we solve the equation what number X actually is, we didn't know that what we were really doing here when we multiplied both sides times the LCD is we were really multiplying each side of this equation times 0. Because now in this case we weren't, but let's say that when we solved this we had got X equal 1. Then here's what would have been going on. If we had got X equal 1, it would mean that this thing had no solution. But how is it that we came up with a solution X equal 1? Well, it's because when we multiplied both sides times this, we didn't realize at the time 2 times X minus 1 is actually the number 0 if X turns out to be 1. Do y'all see that? And so really what we would have done is multiplied both sides of the equation times 0. Y'all look at this. Do you agree that that equation is just false? It's just a false statement. But if I multiply both sides of it times 0, I get a true statement. Y'all see that? But that doesn't change the fact that the original statement was false. So that's kind of what's going on when you solve these. If you do wind up with that restrict, we didn't in this problem, but if you do wind up with that restricted value, the reason that happened is because we didn't realize we were multiplying both sides by 0. Right? So you just have to be kind of cautious about that. Okay, one more problem, then we're going to take our break. And then we're going to come back and start looking at section 1.4. So here, what I want to talk to you all about is, so we're beginning to look at this idea of factoring. This is one of the easiest ways to factor, but let me tell you all first of all, if I have something like this, okay, try to do this quickly because I'm trying to make us not late for break and still get through this problem. So y'all hang with me. We're going to do a little more review over this probably next week. But for now, we're not going to learn how to factor this particular thing tonight unless you already know. But I want to show you what we mean by factoring. So first of all, when we talk about factoring polynomials, a polynomial is just some expression where every term just looks like something times x to a power, like 1x to the second power, 4x, or as a constant term. Factoring a polynomial is kind of similar to how we factor a number. So if I had the number, for instance, 35, and I told you to factor it, you might tell me 35 is 5 times 7. And you would say, I factored the number 35, right? You've written it as two numbers that when multiplied together give you that number back. Well, what we want to do if we're going to factor this polynomial is we want to write it as two polynomials that when multiplied together give me this original polynomial back. This particular polynomial, this type of polynomial, is called a quadratic trinomial. That's not particularly important other than the fact that factoring quadratic trinomials is like a huge part of stuff we need to be able to do in algebra. It pops up, the need to be able to do that pops up all the time. Really not just in algebra. I mean, it pops up in geometry and trigonometry and calculus and differential equation. It pops up in everything. But it's called quadratic because it's second degree. Now, quad means 4, so I'll try to give you the brief explanation, unlike my poor Monday night class. Quad means 4, so it seems like that's what you would call it if it had x to the 4th power. When you have x to the second power, we call it quadratic. The reason is when you raise something to the second power, y'all are familiar with, like, if I have 5 to the second power, y'all know that a lot of times I'll just say 5 squared, right? 5 squared. Well, the reason when we raise something to the second power, we say square is because multiplying a number times itself, raising that number to the second power, the first place that was ever widely used was when you find the area of a square. So, find the area of a rectangle, you multiply the length times the width. But a square is a rectangle where the length and width are the same. So you multiply the length times the length, or raise the length to the second power. So when we say 5 squared, that's because we're really shouting back through the fog of history back to, say, the ancient Greek or even the ancient Egyptians, who knew that when you multiplied a number times itself, you're finding the area of a square, that's that many units long on a side. And the Greek word for square is quadros, which means basically 4 regular or equal sides. Quad 4 ros means regular or normal. So quadratic, when we say it's quadratic, we mean it's a squared polynomial. Trinomial means it has 3 terms, x squared, 4x, and negative 12. Here's what I mean when I say factor this. See how I've written this as 2 polynomials, x plus 6 and x minus 2, that I claim that if I multiply them together will give me this original one back. Just like I claim if I multiply 5 times 7, it'll give me 35 back. And hopefully you remember that to multiply these, you distribute. Some of you may think of it as FOIL, which we'll probably talk about more, a little bit more next week. But really, we're just distributing. We would go x times x, which is x squared, x times negative 2, which is negative 2x. So notice how I distributed that x term to each of the terms in the second parentheses. Now I'm going to move over to this next term, positive 6, and distribute it. 6 times x is positive 6x. 6 times negative 2 is negative 12. Now I've distributed the second term and I've run out of stuff to distribute. So I'm done multiplying, but I need to simplify by combining these like terms. And notice negative 2x plus 6x is positive 4x. And sure enough, that's what we started with, right? So then we know that the correct way to factor x squared plus 4x minus 12 is x plus 6 times x minus 2. Everybody with me? Okay. So back to this particular problem here. I can't remember if I wrote anything about this. I didn't. So we know we got to have a factor of x plus 1 in the LCD, and we know we have to have a factor of x minus 1 in the LCD. And notice those are not the same, right? And in fact, if x is 5, you can see that this number would be 6, but this number would be 4, right, or whatever. So because those are different numbers, we're going to have a factor of x plus 1 as part of our LCD. And we've got to have a factor of x minus 1 as a factor in our LCD. Now the question is, do I also need a factor of x squared minus 1? And so here's our next little factoring trick. What if I have something like x squared minus, 9, let's say. Does everybody agree that 9 is the same as 3 squared? 9 is 3 to the second power. So I've got x squared minus 9, or if I wanted to, I could write that as x squared minus 3 squared, right? Kind of weird, but we could do that. It turns out that anytime you have something that looks like this thing is called a difference of squares. Called a difference of squares for a real simple reason. A square is something raised to the second power. Well, I have 2 squares here. I have x squared, that's a square, and I have 3 squared, that's a square. a difference is the answer you get when you subtract two things, right? So notice this is subtraction. I'm taking the difference of these two squares. So anytime you do that, it turns out anything, if I have anything that looks like a squared minus b squared, in other words, anything to the second power minus some other thing to the second power, it always factors this way. The first thing plus the second thing, a plus b, times the first thing minus the second thing, a minus b. And that is called the difference of squares formula. It's a factoring formula. It works every single time. So that tells me then that if I want to factor x squared minus 9, which is the same as x squared minus 3 squared, well, my a is x, and my version of b is 3. It's going to be a plus b, x plus 3, times a minus b. That's going to be x minus 3. Y'all see? Super easy to factor. By the way, if you FOIL it or distribute it, maybe we'll do it real quick. If I multiply this out real quick, notice what happens. X times x is x squared. X times negative 3 is negative 3x. Then I go to positive 3 times x, that's positive 3x. Positive 3 times negative 3, there's negative 9. And notice negative 3x plus 3x is 0. That cancels, and I just get x squared minus 9. Everybody see that? So, okay, we need to be able to factor a difference of squares. And I think that's what we have here. Do y'all see that? Does everybody see that x squared minus 1 is the same as x squared minus 1 squared? 1 squared is 1. And so this is going to factor as x plus 1 times x minus 1. Y'all see that? So just to save a little space and time, y'all look. Where this says x squared minus 1, if I had a pencil, I would erase that right now. And over that, I would write x plus 1 times x minus 1. And so do you see then that that actually ends up being the LCD? So I know I got to have x plus 1 times x minus 1. But what this tells me is I don't have to multiply anything else times that, because that's literally what I already have here. Y'all see that? So I'm going to multiply both sides times that LCD. And of course, I didn't leave much room to do that. Pretend like those are written side by side, all over one. So on this side, I'm not even going to bother to write that in. Remember, x squared minus 1 squared literally is x plus 1 times x minus 1. And I'm going to cancel all of that with all of that. Y'all see? And it's just going to leave 2x on the right side. On the other side, oh, before we get any further, dang it, what are the numbers that I want to make sure I check for? What are the numbers that I could plug in place of x that could make these denominators 0? 1 minus 1 is 0. What about here?
-1.
-1. So -1 would cause this denominator to be 0. By the way, -1 would cause that one to be 0 too, because notice -1 squared is 1, and 1 minus 1 is 0. And then +1, of course, would make this one 0 or this one 0. So we got to make sure we remember x can't be equal to -1 or +1. Okay, so anyway, we multiply the LCD on the right, we just get 2x. Here on the left, when I multiply this LCD times 2 over x plus 1, this x plus 1 is going to cancel with that x plus 1. Do y'all see that? Try not to cross through it all because I'm distributing. But I still have to multiply that other factor, x minus 1 times 2, and I need to distribute. So I'm going to go 2 times x is 2x. And 2 times -1 is -2, so I'll have 2x minus 2. Then when I multiply all of this times that next term, this time the x minus 1 cancels, but the x plus 1 doesn't. And notice I've got to multiply x plus 1, not times 1, but times negative 1, right? So that's also really just distributing. Negative 1 times x is negative x. And negative 1 times positive 1 is negative 1. And so now I need to simplify this left-hand side. 2x minus x is just x, or 1x. Negative 2 minus 1, be careful with your signed arithmetic. Negative 2 minus 1 is negative 3. So I get x minus 3 equals 2x. It looks like the quick way to solve this to me is just going to be subtract x on each side. You know, that's the same as 1x. So I get negative 3 on the left, and 2x minus 1x is 1x, which is just x. And so that's actually my solution, negative 3. And that's not one of my restricted values, so I know that is the solution. Again, as long as I'm confident I haven't made any errors. Everybody will see it?
Yes.
Sorry about that. Yeah, whenever that happens, y'all just shout right out. I just wasn't paying attention. Story of my life. So, brief recap. We know the square root of 4 is 2. We know the square root of 9 is 3. We're trying to figure out the square root of 50. Here's what we can do. It turns out that if you have a number like the square root of 50, the square root of 50 is equal to the square root of 5 times the square root of 10. In other words, you can multiply what's under the square roots here. The square root of 5 times the square root of 10 is literally equal to the square root of 5 times 10, which is 50. So this is another way of writing the square root of 50. I don't like this way. It's not going to help me. The reason it's not going to help me is just like I don't know exactly what the square root of 50 is, I also don't know exactly what the square root of 5 is, right? It's bigger than 2. It's smaller than 3. I don't know what the square root of 10 is. It's a little bit bigger than 3 because 10 is a little bit bigger than 9, right? But what if I said that this is the square root of 50? What if I said that the square root of 50 is equal to the square root of 25 times the square root of 2? Does everybody see that 25 times 2 is 50? So the square root of 25 times the square root of 2 is equal to the square root of 50. Here's why that helps me. I don't know what the square root of 2 is. It's an irrational number. It's, if you punched it in on your calculator, the square root of 2, it would tell you it's 1.414 blah, 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 blah. But it's 1.414 dot, dot, dot. The digits after the decimal point go on forever. So I can't tell you exactly what the square root of 2 is, but I do know exactly what the square root of 25 is, right? It's 5, because 5 squared is 25. So the square root of 25 is 5 without the square root symbol. So the square root of 50 then must be 5 times the square root of 2. Y'all see what I'm saying? So this is what the square root of 50 looks like if I simplify it. Really see that? And so you can see that what the trick is when you're going to simplify a square root, you know, if it's a perfect square like 4 or 9 or 25, you just write the number down. It's 2. The square root of 9 is 3. The square root of 25 is 5. If it's something like this, you want to see if there's a way to factor this number so that one of those factors is a perfect square. And in this case, 50 is 25 times 2, and 25 is a perfect square. So the square root of 50 is the square root of 25 times the square root of 2. And of course, we know what the square root of 25 is. It's 5. So 5 times the square root of 2. And that's what we're going to say the square root of 50 is equal to. And again, you could get an approximation. Like if you punch in 5 times the square root of 2, You're going to get 5 times 1.414 dot, 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 and whatever you get is going to be essentially going to be the square root of 50 out to however many decimal places. But we want to just leave it like this. Okay, and we'll see some more examples as we go through the course, especially in the next section, where we need to be able to simplify something like the square root of 50. So we'll get a little bit more practice. But now, notice I haven't filled in some of these. So the square root of 4 is 2. What is the square root of negative 4 then? If the square root of 4 is 2, what's the square root of negative 4? Well, it can't be positive 2. Do y'all agree? Because positive 2 squared means positive 2 times positive 2, and that's positive 4, not negative 4, right? Could it be negative 2? Could the square root of negative 4 be equal to negative 2? I think, unfortunately, it cannot, and here's why. If we say that the square root of negative 4 is equal to negative 2, then do y'all agree that what we're claiming is that negative 2 squared is equal to negative 4, right? But it's not. Negative 2 squared is equal to, that means multiply negative 2 times itself, right? It's equal to negative 2 times negative 2. But isn't negative 2 times negative 2 equal to positive 4? Negative times negative is positive. It's equal to positive 4, not negative 4. Then this must not be right. It turns out that negative 2 is actually just the other square root of positive 4. It turns out that positive 4 has 2 square roots. It has a positive square root, 2, and there's a negative version of the square root of positive 4, which is negative 2. Why? Because both of these numbers, 2 squared is equal to positive 4, negative 2 squared is also equal to positive 4. So those are the 2 different square roots of positive 4. Negative 4, we got a problem. We're going to have a similar problem when we try to find the square root of negative 9. We'll have a similar problem when we try to find the square root of negative 50. And so if we just kind of want to see how this problem shakes out, don't hang with me half a second. I decided I'm getting tired of that marker. I kind of am a little bit OCD, and when my marker starts drying out, it starts like scratching, sort of like fingernails on a chalkboard on my paper, and I can't take it anymore. So get a new one. So let's look at some of these negative situations. So we had the square root of negative 4, or the square root of negative 9, or the square root of whatever, negative 16, and so on. Okay, so here's what I can do if I'm trying to figure out what to do with the square root of negative 4. You can see that the problem we're having in finding the square root is that negative under the square root symbol, right? And some of you may remember having been taught in, say, a pre-algebra or an Algebra 1 course back in high school. You might remember at some point having been taught that you can't take the square root of a negative number. If they did teach you that, it's unfortunate, because you can take the square root of a negative number. But there is no real number that's the square root of negative 4. The only candidates are 2 and negative 2. Those are real numbers, but neither one of them is the square root of negative 4, because either of those numbers, if you square it, you get positive 4, not negative 4. But we can at least do this. Remember how we were simplifying that square root of 50? What if we do a similar thing here? What if we say that the square root of negative 4 is equal to the square root of positive 4 times the square root of negative 1? 4 times negative 1 is negative 4, right? Well, this must be sort of another way to write the square root of negative 4. This actually helps me a little bit, because I do know what the square root of positive 4 is. We just looked at it. The square root of 4 is 2. The problem is I don't know what the square root of negative 1 is, right? The square root of 1 is 1, because 1 squared is 1. The square root of 1 could also be negative 1. The negative version of the square root of positive 1 is negative 1, because negative 1 squared is also positive 1. Do y'all agree? So then I know the square root of negative 1 isn't 1 or negative 1. It must be something else, and I don't know what the square root of negative 1 is. So for now, I'm just going to leave that like it is. But at least I simplified it a little bit, right? And I could do a similar thing with the square root of negative 9. It will be the same as the square root of positive 9 times the square root of negative 1. And we know what the square root of positive 9 is. It's 3. So the square root of negative 9 is 3 times the square root of negative 1. The square root of negative 16. Just kind of beating a dead horse here at this point. It would be the square root of positive 16 times the square root of negative 1. The square root of 16 is 4, right? Because 4 squared is 16. So the square root of 16 is 4 times the square root of negative 1, which is kind of an I don't know thing. By the way, we could do a similar thing if we looked at the square root of negative 50. In this case, I'm going to say that the square root of negative 50 is equal to this. It's equal to the square root of 25 times the square root of 2. Now remember, that's equal to the square root of positive 50 times the square root of negative 1. So all that multiplies to be negative 50. So this is a way I could write the square root of negative 50. And I could say that the square root of 25, we've seen, is 5 times the square root of 2. So remember, that's how we simplified the square root of 50, positive 50. But we have that times the square root of negative 1, right? So the point is, if, you know, I know you're probably like, okay, can you get to the point? Okay. So when I try to take the square root of a negative number, you can see that in every single case, the problem I have really can be sort of collapsed down to one single problem, which is there's no such thing as the square root of negative 1. Y'all see that? So that really is the problem in taking the square root of a negative number. It's that any negative number has negative 1 as a factor, and we don't know the square root of negative 1 because there is no real number that's the square root of negative 1. So here's what some guy did. This probably happened back in maybe the 13th century, maybe in Italy, maybe even earlier, but probably in Italy. I'm guessing, there's a reason I'm guessing it was an Italian mathematician. It's because in like the 1200s in Italy, there was a group of mathematicians there that were beginning to work on how to solve what we're going to call polynomial equations, where you're solving an equation that has like not just x, but maybe x to the second power, or term with x to the third power, or x to the fourth power in it, and so on. And it turns out that these kind of numbers, where you're trying to figure out the square root of a negative number, they pop up a lot when you're trying to solve those kinds of equations. And you come up with a solution that looks like this, the square root of negative 4 or something. And so I'm guessing that it was some Italian mathematician. At first, when they would run across those problems, here's a simple example. Let me just show y'all where this could come from, and we'll see sort of what they chose to do as their solution to figuring out the square root of negative 1. If I wanted to solve this problem, there's multiple ways to do it. But one way to do it is, it's kind of similar to what we were doing with those linear equations in 1.2. What if I add 9 to each side? That gives me x to the second power equals 0 plus 9 is 9. Now, I'm trying to solve this equation. I'm not trying to figure out what x to the second power is equal to. I'm trying to just figure out what number x is. But do y'all agree, based on what we've said about square roots, if I were to take the square root of x to the second power, I would just get x, right? Because remember, y'all listen real carefully to this. When we say the square root of x squared, that is going to be equal to whatever I would raise to the second power to get x squared, right? Well, obviously, the thing I would raise to the second power to get x squared would be x, right? And so it turns out, this is not theory, this is just, here's a way to think of it that always works. If you take the square root of a square, it's kind of like the square root and the square literally just cancel each other out. Y'all see that? But if I take, this is that little basic rule of equations, the golden rule of equations. If you take the square root of the left side, you have to take the square root of the right side as well. And by the way, we've seen this already. Remember, 9 has two different square roots. It has a positive square root and also a negative square root. And both of those numbers are going to turn out to be solutions to this equation. So when we solve an equation like this, we always want to put that little plus or minus symbol in front of the square root to say that we want the positive version of the square root of 9, which is 3. But we also want the negative version of the square root of 9, which is negative 3. Everybody see? And by the way, notice that equation, which remember was x squared minus 9 equals 0. Notice that equation doesn't just have one solution like those problems we saw in section 1.2. It's got two different solutions. Y'all see that? It's a second degree equation. It has two solutions. When we were working with those first degree equations in 1.2, it always had one solution. Second degree equations typically have two solutions. That's not a coincidence. Turns out that third degree equations generally have three solutions and so on. At any rate, that was easy to solve, right? Once you saw that you could just get x squared by itself and then take the square roots of both sides, that gives you the solutions. But what if I did this problem, which is almost the same problem? Well, if I try to use that same approach, then I'm going to move this 9 to the other side, just like here I moved the negative 9 to the other side. But to move this positive 9 to the other side, I have to subtract 9 on each side, right? And when I do, I get x squared equals, well, 0 minus 9 is negative 9. And so you can see how these mathematicians, when they start working on, for instance, solving second degree equations, run into that situation. Because remember, what we did to solve that equation was we took the square roots of both sides. If we try that here, remembering that every number has a positive and negative square root, I get x equals plus or minus, well, remember the square root of negative 9, it's the same as the square root of positive 9 times the square root of negative 1. So I get plus or minus 3 times the square root of negative 1, and that's as far as I can go. Y'all see that? And so these mathematicians had been doing this for a long time. And when they ran into equations like this, and they come down to this point where they realize that the solution is going to involve the square root of a negative number, they would just say that that equation is nonsensical. Like, okay, technically we can say that this equation has solutions, but these numbers don't really exist. There's no such thing as the square root of negative 1. So the solutions are nonsense, and they would just kind of throw those equations to the side and say, you know, we'll just not worry about these equations, right? And most of y'all are saying, well, I think that's a good idea. But nowadays we worry about them. And it turns out there's a reason to worry about them. It's because, and if I have any engineering majors, you're probably going to see this. And if I have any physics majors, you're going to definitely see it as well. it turns out that these kinds of equations, while they may not result in real number solutions, it turns out that equations like that actually do matter. Because remember, a lot of what we use mathematics for is to try to model things that actually happen in the real world around us. So, for instance, when you see, hurricane whatever is barreling toward the coast, and they've got all these little projected tracks for it, and they've got their little cone of uncertainty where they're trying to predict where and when it'll make landfall. Well, the way they're coming up with that is they've got a supercomputer with a massive system of equations that they have built to model the weather. They pour all the data they have about that storm into that system of equations, and it solves the system of equations, and the solution it spits out is a projected storm track. It turns out that for those systems of equations to work, they can only work correctly if they include equations that have solutions that involve these numbers that are not real numbers. So some of y'all may remember that type of number, we often call them imaginary numbers. It's unfortunate that we call them that, because first of all, real numbers are imaginary as well. Like the number 2 is not a thing, right? It's not, like, what is 2? I mean, it's not a concrete object. It's an idea. Like 2, it might be a symbol that represents the cows in my pasture, or it might represent the shoes on my feet, or it might represent the hands at the end of my arms. It might represent the students on the back row in the Greenville classroom, but it's not a real thing. It's not real. We call real numbers real because we use them to quantify collections of real sets of objects, right? The real numbers are actually an abstract idea. And by the way we talk about abstraction in math is similar to how we talk about it in art. So if you've ever gone to an art museum and you're looking at abstract art, you might not be like an art major or an art historian, and you may not, like off the top of your head, have a perfect definition of what is abstract art, but it's one of those things you kind of know it when you see it, right? And so, like you look at a portrait by Pablo Picasso and it's, whatever. Use my great art skills here to do a Picasso. You see something like that, like you see a portrait by Picasso, okay? Maybe like that. Then when you see that, you're like, okay, either one of two things or both are true. Either this guy can't draw or this is abstract art, right? Incidentally, it turns out Picasso was an excellent artist in terms of his ability to reproduce realistic, lifelike paintings. Before he got into his Cubist period, he actually painted portraits for a living, and they actually looked like actual portraits of actual people. So he did this kind of stuff on purpose. But here's kind of one way to think about abstract art. Like when you look at this thing, first of all, clearly, this doesn't look like any particular person. But does everybody agree that when you look at it, you can sort of see it's supposed to be a woman? But like if I were to say, Larissa, that's my sketch of you, you would be very offended, and rightly so, right? And any woman would be rightly offended. But because it doesn't look like any woman, and it's clear that it wasn't intended to look like any particular woman, then maybe it becomes a symbol to represent the idea of woman. And I know that sounds crazy, but look, we got abstract art in our building, and you've all seen it all the time. You never give it a second thought. But I know that when I need to go to the restroom, I generally go to the one that has that little picture, whereas probably you ladies, if you go to the bathroom, you probably generally go to the one that has a little picture kind of like this one. You know, something like that. The Picasso looks more like a woman than that, but you know, y'all get the idea, right? It's like, I don't know what man that is, but I know that when I have to go relieve myself, that's the room I should go in to do it. Ladies, you probably go in this room. I'm saying probably because we already talked about it break. I need to stay away from politics. I need to stay away from gender discussions. Frankly, ladies and gentlemen, y'all use whichever restroom you want. I couldn't care less. Close the stall door. Ladies, probably going to be more complicated for you to use the urinal than it is for us men. But on the other hand, if you manage to use it, you might be less likely to pee on the floor than us. Who knows? At any rate, there was a point I was making in here somewhere. Oh, imaginary numbers. So look, they're imaginary. Oh no, well, how am I supposed to deal with imaginary numbers? I'm having enough trouble with the real numbers. Real numbers aren't real. We call them that because we can use them to count collections of real, actual concrete objects. You know, it wouldn't make sense to say I have 3 times the square root of -1 cows in my pasture. But it turns out that a lot of natural processes, like the way that air swirls in a tornado or hurricane, which is very similar to the way that water swirls in a whirlpool or when you flush it down your toilet, except I think they maybe go in opposite directions. The way that water flows down a riverbed, or the way that air flows over the wings of an airplane wing, which, by the way, are also 2 things that are pretty similar to each other. If you want to model that stuff and simulate it, say on computers, you have to use math that includes this type of number, okay? So while these numbers may not be what we think of as real numbers, they do model things in the real world, just like real numbers count things in the real world. So finally, what do we do with all this? Well, here's what this Italian guy said, and I'm just making this up in my own mind. It's the way I kind of think about it. This Italian guy at some point said, look, I know we've just been ignoring equations that leave us with these kind of numbers as solutions, but what if we didn't? What if we were going to think about these types of numbers? And so I guess what he thought, and by the way, ladies, I'm not trying to be sexist. I'm saying he because I try not to be sexist, but the mathematicians of the 13th century, they didn't try not to be sexist. They were pretty much all men. And if there was a woman mathematician, she was probably doing her math in secret so she didn't get like torched for being a witch or something. Y'all with me? So anyway, he said, what if there was a square root of -1? What if we just imagine that there is such a thing? Well, the first thing we're going to have to do is have some symbol to represent it. So he said, well, since I'm just imagining that there is such a thing, I'll just use the letter I. And so when you see this in any kind of math text, it'll always be a lowercase italicized letter I. We use that as a symbol that simply represents the square root of -1, which we know it doesn't really exist, but we're going to imagine that it does. So everybody just kind of cool your brain down a minute and don't like freak out on the philosophical implications of that. We're going to roll with it. So now that means then that anytime I'm taking the square root of a negative number, I know how to do it. The square root of -9, well, we know it's the square root of 9 times the square root of -1. And anytime we have a square root of -1, we're just going to call it I. So it's 3i. Negative 16 is the same as the square root of positive 16, except with an I after it. Square root of 16 is 4, then the square root of negative 16 is 4i. The square root of negative 25 would be 5i. And the square root of negative 49 would be 7i, and so on. And the square root of negative 50, y'all look at how we're going to write this. So here's the square root of negative 4. Here's the square root of negative 9. Here's the square root of negative 16. Here's how we're going to write the square root of negative 50. We're not going to write it like, if you look at what we have here, you would think we would just write 5 times the square root of 2 times I, right? But we're not going to quite write it that way. It's not that this is incorrect, but it is customary to write it this way instead. These are the same thing, because remember, multiplication is commutative. 2 times 3 times 4 is the same as 4 times 2 times 3, or whatever order you want to write it in. The reason we would do something like this when we simplify the square root of negative 50 is because if I wrote it like this, where I put the I at the end, it's kind of hard to tell, especially with my sloppy penmanship. It's kind of sometimes hard to tell, is that I, was it intended to be under the square root with the 2, or was it intended to be outside the square root of 2? Well, it's intended to be outside the square root of 2, but if you just write it like this, then there's no question of that, right? So typically, when you're writing what we'll sometimes call these imaginary numbers, when you're writing a number like that that has an I in it, typically you will write the I after any integer part. Like I wouldn't write I2 here, I would write 2I. Or I wouldn't write I3, I'd write 3I. Here I wouldn't write I5, I would write 5I. So we'll put, sorry, I wouldn't write I before the 5, I'd put the 5 before the I. But I would put I immediately before any square root that's in that thing. Everybody see that? So that's just kind of customary how we would write it. So that means now we can find the square root of any negative number. I know it feels less than satisfying to do it, because really all we're doing is we're finding the square root of the positive version of that number, and then we're just putting an I after it, right? But literally that's what we do. But as we do that, always remember that that little I is a symbol that represents the square root of negative 1. Okay, so now, I know that took forever to talk about, but we're getting somewhere here. So here is what your text will call a complex number. This is called standard form for a complex number. A plus BI, that's A plus BI, where A and B, this AB, that is the little symbol, is an element, is an element of the set of real numbers. So a complex number looks like A plus B times I, where A and B are each real numbers. And of course, I is that little symbol that means the square root of negative 1. This number A, we always call that the real part of the number. This number B, notice that's the one that's attached to the little I part. So B, we call that the imaginary part of the number. So here's an example of a complex number. So that's not two different numbers, that is one complex number. A complex number has two parts. It has a real part, 2. It has an imaginary part, 3. And it's 2 plus 3 times that little imaginary unit, the little I, which represents the square root of negative 1. That is a single complex number written in standard form. So here's the thing about the complex numbers. You know those real numbers that we're all used to working with for basically our whole lives? Like, I don't know, my favorite number, 5. I don't know why it's my favorite number, it just always has been. 5 is a real number. Everybody agree? 5 is also a complex number. Here's how I know that. Because to be a complex number, a number just has to look like some real number plus some other real number times I. Do you agree that 5 is the same thing as 5 plus 0 times I? 0 is a real number, and 0 times anything is 0. So 5 plus 0 times I is 5 plus 0, which is 5. This is just another way to write the real number 5. But it is technically written in the form of a complex number, whose real part is 5 and whose imaginary part is 0. So it turns out that the set of real numbers, the numbers that we're used to working with, are actually just the subset of the complex numbers that have 0 for their imaginary part. In other words, any real number, 1/2. Well, that's a real number. It's a rational number, 1/2. But that's the same as 1/2 plus 0i, which means technically that's a complex number, right? So every real number is a complex number. Of course, not every complex number is a real number. This one's not real, right? Because it's got a non-zero imaginary part. And then those numbers we've just been looking at, like 2i, 3i, 4i, and so on, these numbers are sometimes called imaginary numbers or pure imaginary numbers. Imaginary numbers also belong to this set of complex numbers because do you agree that 2i is the same as 0 plus 2i, for example? And so I've written it in that a plus bi form where a and b are real numbers, right? A is 0, that's a real number. B is 2, that's a real number. So what we think of as the imaginary numbers, they're just the subset of the complex numbers that have 0 for their real part. What we think of as the real numbers is just the subset of the complex numbers that have 0 for their imaginary part. Then we have numbers like these. These are complex numbers that are not real numbers because they have a non-zero imaginary part. It actually would not be proper to call these imaginary numbers because they have a non-zero real part. At best, we could just say, we've got a couple of options. We could just say it's a complex number. Now, complex number isn't really descriptive all that much. Now that we see that when I say complex number, I might mean a real number, or I might mean an imaginary number, or I might mean a number that's neither real nor imaginary. Complex number covers a lot of ground, so a lot of times we'll just call this a non-real number. Everybody with me? So just in terms of like vocabulary, language, and like, so you'll know what I'm talking about. When I say non-real number, technically, generally, I'm speaking about a number like this. It's not a real number. But usually if I say non-real number, I also mean it's not really an imaginary number either. It's one of those complex numbers where the real and the imaginary part are not 0. Everybody with me? Okay, so let me tell you what really section 1.4 is about. Really, the brunt of section 1.4 is about, now that we've seen the idea of a complex number, you know, when you first learned about numbers, what was the first thing you did after you learned about numbers? Well, you learned how to do basic arithmetic. Yeah, you learned how to count and do basic arithmetic, right? How to add them, subtract them, multiply, divide. When you first learned about fractions, once you learned about fractions, what's the first thing you had to do? You learned to add, subtract, multiply, divide. Well, now we learned about complex numbers. So what we want to do is learn how to add, subtract, multiply, and divide those 10 numbers. And that's really what's going on in most of section 1.4. So I think for sure we can get through addition, subtraction, and multiplication tonight. We may not quite make it through division unless we stay all the way till 9, which I know y'all are dying to do, right? Ooh, so enthusiastic. Well, my Monday night guys, they hung in there pretty late. I'll give them that. I think we can get through addition, subtraction, multiplication. We might have to hold off division for the beginning of class next week. What that will mean, I'm just telling y'all this now, so when we are ready to go, y'all don't have to sit and listen to me. I'll make you sit and listen to me now. What that will mean is that by the time you come to class next week, you'll need to have section 1.2 of the homework finished. And section 1.4, if we don't get the division covered, that means there will be probably 2 or 3 problems at the end of the section that you may not be able to do yet. And that's, never panic when that happens. You know, I just tell you, technically section 1.4 will not be due until the week after we finish covering in class. I just always think it's the best idea that if we've covered part of that section, if you try to at least work through the problems up through the stuff we've done in class, just to keep yourself from maybe getting hammered if we happen to catch a week where we do finish 2 sections in one night. Okay, at any rate, it turns out that adding, subtracting, and multiplying complex numbers is super easy. And I'm saying it's super easy because I think it's going to be intuitive for most of you. I think you, whether you know how to do this or not, I think you kind of already know how to do it, whether you realize you do or not. So here's a complex number, 3 plus 4i. Here's another complex number, 7 minus 6i. And I'm trying to add those 2 numbers together. How do you suppose, if you were just guessing, how do you think we ought to go about adding those numbers? Like, what would you do if I just told you to do that and you were just going to do what seems to make sense to you? Do the 3 plus 7. So if you do 3 plus 7, you'd get 10, right? And then what? The 4i minus 6i. And if I was going to do 4x minus 6x, that would be negative 2x. Do y'all agree? 4i minus 6i then must be negative 2i, like that. Everybody with me? So that's like combining like terms. Would y'all agree? If you do 4i minus 6i is negative 2i, it's like we combined like terms. And in fact, that's what we've done. And in fact, that's correct. So you see what I mean when I say kind of intuitively, you sort of already know what to do. You can think of it like combining like terms. Technically, we should think of it like combining like parts. We're going to combine the real parts. So the real parts of the numbers, 3 and 7, we're going to add those. 3 plus 7 is 10. Then we're going to combine the imaginary parts. 4i minus 6i. And all we're doing is 4 minus 6 is negative 2, and the I stays the same, right? Just like if we had 4x minus 6x, it'd be negative 2x. Everybody see that? So you can see that we kind of already know how to do this. We combine like parts. Subtracting is the same thing, except you have to remember this minus sign is going to reverse the signs in this second complex number. Everybody aware of that? So there's more than one way to do this. You should do whatever works best for you. But you could say the real part first. 3 minus 7 is negative 4. Everybody with me there? But then here's where you got to be careful, because I always have some students who go, okay, and 4i minus 6i is negative 2i. That's incorrect. Does everybody see that it would be incorrect to go 4i minus 6i is negative 2i? What did I miss there? What did I do wrong? Yeah, it's not 4i minus 6i. Y'all look, you can't forget there's a subtract symbol between them. It's 4i minus negative 6i, right? And that's like negative times negative. The negative of negative 6i, that's really plus 6i. Do y'all see that? So really what I've got here is 4i minus negative 6i, which is actually 4i plus 6i, and that is positive 10i. So I actually get negative 4 plus 10i. Everybody see? Everybody good there? So you just got to remember that when you're subtracting anything, that a minus sign outside these parentheses always reverses the signs of whatever's in the parentheses. Everybody with me? So that's how we add and subtract. It's just combining like parts. Everybody good there? Because I'm about to move on to sum and multiplication. Okay. Now let's take a look then and see what happens when we multiply. Trying. Okay, so now I want to multiply. So notice this isn't 3 plus 2i plus 4 plus 3i. It's 3 plus 2i times 4 plus 3i. Everybody see? I think most of you, whether you realize it or not, kind of intuitively already know how to do this as well. So if I were to tell you to multiply these, what would you tell me I should do? Everybody's doing this kind of thing. Y'all are telling me what y'all are trying to tell me with words that evidently you don't have. You want to distribute, right? We want to learn that word distribute because it accurately describes most of the multiplication we do in math. So we want to distribute, in other words, and this is what y'all were telling me with like hand motions going, you know. Here's what y'all were telling me. I need to multiply. I need to start with the 3 here. I need to do 3 times 4. Then I need to do 3 times 3i, right? 3 times 4, 3 times 3i. Then I need to move over to this 2i and multiply it times each of the things in that second set of parentheses. 2i times 4 and 2i times 3i. That's kind of how we multiplied. Remember earlier when we were looking at factoring and we had that thing, what was it? It was x plus 6 times x minus 2 or something. That's kind of how we multiplied it. I'm going to call this FOIL. Some of you know FOIL. Some of you probably don't. You don't particularly need FOIL. What you need to know is what distributing means. But FOIL is one specific example of distributing. It only works when you have 2 things in each set of 2 parentheses. But FOIL is a memory device to help you remember how to distribute this. The reason I'm using FOIL is because it turns out to be useful when we're factoring, to be able to use this sort of little memory device. So you don't have to know FOIL, but I want you to understand what it's saying. So FOIL, first, outer or outside, inner, inside, last. First, outer, inner, last. It's supposed to be a little memory device to help you remember how to do this. And so I'm going to quickly show you how it works as we multiply this. So F, first. The first thing in the first set of parentheses is 3. The first thing in the second set is 4, right? I want to multiply the first thing times the first thing. 3 times 4, which is 12. And of course, that's what happened when I did the F times F part. O, outer. If you look at the 2 sets of parentheses, 3 is on the outer part of the first set of parentheses. 3i is on the outer part of the second parentheses, right? You're looking at those outermost terms or parts. And so I'm going to multiply that outside term times this outside term. Outer times outer, 3 times positive 3i is positive 9i. That's the O, or outer part. Everybody with me? I for inner. Notice 2i is the innermost term in the first set of parentheses. 4 is the inner term in the second set. These are the terms that are on the insides of the 2 sets of parentheses. So we multiply inner times inner term. 2i times 4 is positive 8i. And that's the I, or inner part of FOIL. Finally, L for last, and that's simple enough. 2i is the last term in the first set of parentheses. 3i is the last term in the second set. I need to multiply last term times last term. So 2i times 3i is negative 6, and that's the L part of FOIL. Is that right? Is that right? 2i times 3i is negative 6.
It's a positive.
Positive 6. First of all, make sure you remember we're multiplying, not adding, right? So certainly there's going to be a 2 times 3 equals 6 in there somewhere, right? So I'm hearing plus 6. I think it's minus 6. Okay, Bailey's coming up with a thought here. So first of all, make sure we remember that I'm never wrong. I got to quit saying that because the group here in Greenville can tell that I'm joking when I say that. The people in Paris probably are just sitting there thinking he's an a-hole. Yeah, I'm not never wrong. But I want y'all to think about this because it turns out that 2i times 3i is negative 6. I want you to see why that's true. Bailey is on to something here. When I multiply 2i times 3i, which is what I was doing here when I did last times last. So let's look at that. Well, first of all, 2 times 3 is definitely 6. Do y'all agree with that? A positive 6. But look, you can't ignore the fact that this isn't 2 times 3, it's 2i times 3i. So I can multiply 2 times 3 to get 6, but do y'all see that if I multiply I times I, wouldn't that be the definition of I squared? Just like 2 times 2 is 2 squared, or 5 times 5 is 5 squared, or x times x is x squared. Well, I times I is I squared. So positive 2 times positive 3 is positive 6. I times I is I squared, but what is I squared? Here's where you got to put your thinking cap on. If I say that I is the square root of negative 1, which, by the way, I have said, I've already said that, right? I is a symbol we're using to represent the square root of negative 1. Okay, do you agree that if I have something like, do you agree that the square root of, say, 25, what is the square root of 25? It's whatever number I would raise to the second power to get 25. Do you agree? Well, then do you agree that the square root of negative 1 would have to be whatever number I would square to get negative 1? Well, I say that the square root of negative 1 is I. Well, doesn't that mean that I squared has to be equal to negative 1? Y'all see what I'm saying? By the way, another way to see that is I is equal to the square root of negative 1. Square both sides of this equation. You're allowed to do that. And you know how we said that if you took the square root of a square, the square and square root would cancel out? Well, guess what? They're going to cancel out here too, the square and the square root. And I'm going to see that I squared is negative 1. So do you see why when I said that 2i times 3i, do you see why I said that's equal to negative 6? Because what it's really equal to is positive 6i squared. But I squared is actually negative 1. And positive 6 times negative 1 is actually negative 6. Do y'all see that? That's the entire trick in multiplying these complex numbers. Everything is super straightforward. Do y'all agree? We're just distributing. And it's all super straightforward, except you got to remember that anytime you multiply 2 I terms, there's going to be an I squared involved, which is actually the real number, negative 1, and you can kind of see what happens. 2 plus 3 is positive 6, but in the end, we reverse that sign because we've got an I squared that makes it positive 6 times negative 1, right? At any rate, once we see that, we can now combine like parts. In other words, the real parts. 12 minus 6 is 6. And then the imaginary parts, 9i plus 8i. 9i plus 8i is that 7 plus 17i. And so there's what we get when we multiply 3 plus 2i times 4 plus 3i. Everybody with me? Try this one. I'm going to give y'all a minute to try it, then we'll do it together. But I want to, for those of you who think you're getting the hang of this, I want to give you the chance to see if you are. In the meantime, I'll be trying to figure out what I think it is. So if you do get an answer, I'll be able to let you know if you got it right or not. Okay, I think I know what it is. If anybody thinks they have the answer, just shout it out, and we'll see if we agree with you or not. Anybody? So I guess I could do this. You could use that as kind of a model. Covered that up. I mean, I'll be pretty. Say it again.
Is it negative 25?
What did they say?
Negative 25.
Negative 25. What else?
That's what I got.
You got what?
11.
Negative 25 plus 11i.
I got 45 minus 11i.
Was that Richard that said he got 45 minus 11i? Was that you?
Yes. I'm not confident, but
It's correct. 45 minus 11i is the correct answer. So let's take a look at why. Yeah, it's 45 minus 11i for sure. And when y'all see it, however y'all got the 25, negative 25 plus 11, or whatever y'all got, you'll see why it's correct here in just a minute. So the biggest thing, of course, is when you're doing stuff like this, particularly until you've done it a lot where you're really confident and comfortable with it, the biggest thing is take your time and do it one step at a time. So I know I'm going to start just by going 2 times 5, right, which is 10. That's easy enough. I'm going to do 2 times 7i. That's simple enough too. 2 times 7 is 14, positive 14, right? 2 times 7 is 14 times I. That's just positive 14i. Everybody good there? Sorry, that's 14. I'm sloppy there. Then, we don't have anything else to multiply the 2 times, right? We're going to move over to this negative 5i. And negative 5i times positive 5. Well, negative 5 times positive 5 is negative 25i, right? Then, finally, we're doing negative 5i times positive 7i. I think that's going to turn out to be positive 35, but let's look at why. So negative 5 times positive 7, do y'all agree that that is negative 35, right? Negative 5 times positive 7 is negative 35, but don't forget, we also have I times I, which is I squared. But what is I squared equal to? I squared is negative 1. So this last term, negative 35i squared, is really negative 35 times negative 1, which is I squared. Do you agree that negative 35 times negative 1 is just positive 35? So this minus 35i squared, if we simplify it by saying I squared is negative 1 and negative 35 times negative 1, that's just positive 35. Now can everybody see, if you hadn't already, if you didn't get that answer, do you see why what Richard said is correct? Because now when I combine the real parts, 10 plus 35 is 45. And then the imaginary parts, 14i minus 25i. Well, 14 minus 25 is negative 11. So 14i minus 25i is negative 11i. Let me see how that goes. Y'all kind of getting the hang of this now. We're going to look at one more problem, and we're going to go home. Best news y'all have heard all night, right? One more problem, then we'll go home. If I can get my papers sorted together here. Okay. So those of you who struggled with that last one, if you didn't quite get the right answer, I'll bet that if you did that last one and you didn't get the right answer, I'll bet when we then went through it together, I'll bet at some point you went, oh, I see where I went wrong. So you probably got it now. So everybody take a minute and do this one and see what you get. I'm going to predict the answer, and I want y'all to check and see if I'm correct. I think the answer is going to be 34 without any I's at all. I think it's just going to be the real number 34. But y'all do the problem and tell me if that's what you get. And then we'll look at it together. And if the answer is 34, that seems weird because that's just a real number. So we'll need to talk just briefly about why that happened if I'm correct. Must have coffee. Paris, once again, I got it back. All right, so I saw Celeste look like she was working. Paris, y'all working? Has anybody got an answer there in Paris yet?
I got 34.
You got 34?
Yes.
Check your signs if you got negative 34. You got 34? I heard somebody in Paris saying they got 34. Celeste, did you get 34? Have you been able to get through it?
Yes, I did.
You did? Okay. All right, let's real quickly take a look at why this turned. It's 34, which seems weird because these are not real numbers. Let's take a look at what happened here. First of all, let me say this. These two numbers, let me get back to that camera. 3 plus 5i and 3 minus 5i. Numbers like that are called complex conjugates. And you don't have to worry, we'll talk about that here in a minute. Conjugates, C-O-N-J-U-G-A-T-E-S. Complex conjugates are numbers that look like A plus BI and A minus BI. So in other words, when we say that two numbers are complex conjugates, we mean that they're the exact same complex numbers except the sign of the imaginary parts is opposite in the two numbers. So make sure you see exactly what's happening here. The sign of the real parts is exactly the same. Everybody see that? The sign of the imaginary parts are exact opposites. The imaginary parts are exactly the same except their signs are opposites. So the real parts are exactly the same. The imaginary parts are exactly the same except they have opposite signs. If we multiply these out, and I suspect those of you who did this and got 34, you just multiplied it out, which works perfectly fine. If you do that, 3 times 3 is 9. 3 times negative 5i is negative 15i. Then you move over to the 5i. Positive 5i times 3 is positive 15i. Of course, you can see what's going to happen to those i's already, right? And then positive 5i times negative 5i, remember that's going to be negative 25i squared, right? But I squared is negative 1, and negative 25 times negative 1 is positive 25. And those two, negative, because of the fact that these are all the same except the imaginary parts are opposites, when you do the outside and the inside parts of FOIL there, you always get exactly the same I term, but with opposite signs. And of course, when you combine those, you get 0, they cancel, and you just get 9 plus 25, which is 34. Y'all see that? Here's what I want y'all to show us, I want y'all to see about the complex conjugates. When you have this situation, it's the only time this works. when you have a situation where you're multiplying two complex conjugates, it turns out that there's a shortcut that works every single time. If you just square the first number, everybody see 3 squared is 9. Square the second number, 5 squared. Just look at the number 5. 5 squared is 25. And you add those numbers together, that always turns out to be the answer. And again, you can see why it works. It's because the other terms that you get cancel each other out every time. And notice when I did the first times first part, 3 times 3, that was the same as just looking at this 3 and squaring it, right? And when I did the last times last part, positive 5i times negative 5i, I got negative 25i squared. But that turns out to just be what would happen if I took this number 5 and squared it, because it turns out to be positive 25. Everybody see that? So what that means is, if we have a problem like this, I could go through the whole process of multiplying it. There's nothing wrong with doing that. But I also know that these are complex conjugates, so I could just square the first number. 7 squared is 49. I could square the second number. 4 squared is 16, and add those numbers together. That's 59. Is that 65? Then I guarantee you when we multiply these, we'll get 65. Now, last thing before we leave. I know y'all are looking at this complex conjugate thing going, okay, well, that's a trick. It is a trick. And sometimes when we teach you tricks in math, they're dumb tricks. They're dumb because they work in some one specific little circumstance that hardly ever pops up, and you would be better off to just understand how math works than try to memorize 500,000 different little rules that only work occasionally in certain situations. It would be better to know some general rules that always work. The reason that I want y'all to know this little shortcut is because it turns out that there's a situation that happens that requires us to multiply complex conjugates a lot. And what that situation is, it's when you divide one complex number by another complex number. Now that's where we're going to pick up next week. But it turns out that to be able to divide one complex number by another one, and one of the intermediate steps in accomplishing that is almost always you end up having to multiply some complex number times its conjugate. And it's nice because we have to do that every time we do a division problem. It's nice for there to be a shortcut that lets us do that real quick.